All right, so we're kind of starting off today, and it's going to feel a little bit disjointed here initially, just because we're kind of marrying together a couple of different concepts here at the same time. And especially given that we covered some of this ground in lab yesterday, we're going to see a little bit of reinforcement happening here as we go. So if you recall, the primary focus yesterday was all about the concepts of internal energy, heat, and work. And then at the very, very end, we got into some properties talking more about enthalpy itself, the heat of reaction. And looking at that heat of reaction as an extensive property, one that changes with the amount of stuff that we have. Well, what we're looking at now is we're starting to look at processes and how the heat energy fits into that mold. So let's take a look, just for example here, at what we would have to do to turn ice into boiling water. So if we started with snow down here at -18 Celsius, in order to get it up to the point where we could boil it, we'd have to undergo several processes. First, we'd have to heat it from that -18 degrees up to the melting point of snow, ice, so 0 degrees. That would be one heating phase. We would also have to convert all of that solid into liquid. That would require heat energy to redistribute those hydrogen bonds, make them more disordered as we go from the highly ordered solid state to the less ordered liquid state. That's going to require energy. Once we've got all of that conversion at the molecular level, then we've got to heat it up again to the boiling point. That's going to require more energy. And then once it's at the boiling point, we're going to have to add even more energy, because now we got to break all of those hydrogen bonds that are holding it in the liquid phase so that it can become a gas. And so that's going to require even more energy there. And then if we continue to heat it, to get the temperature up, obviously we're going to have to heat it and heat it and heat it. This kind of graph is known as a heating curve. And what it is showing is that this process of conversion requires several different stages of heating. Now, if you just take snow and put it into an Erlenmeyer flask and heat it on a Bunsen burner, you're not actually going to see all of these as distinct steps. You're just going to see, oh, the snow melted. Now it's boiling. But in reality, there are different stages here. And each one of those stages would require a different calculation to figure out how much heat needed to go into that substance. And so one of the things that we can look at that would help us to frame this calculation is the concept of heat capacity. Heat capacity is merely the amount of energy that it takes to raise the temperature of an object by 1 degree Celsius. Now notice that that heat capacity isn't standardized in any way. So if I'm comparing pieces of plastic, a heavier object is going to have a larger heat capacity than a lighter object if they're made out of the same material, because the heavier object has more stuff to heat up. So it's going to require more energy to get that same 1 degree uptick than the lighter object would. And so this has obvious implications and limitations, because without any kind of standardization, it's really hard to compare. This object requires 500 joules. This object requires 5 joules. Why the difference? And so that's where we can get into more specific values. Specific values like specific heat capacity. Notice the difference here, again, in our capitalization. Heat capacity is given a capital value. Specific heat is given a lowercase value. Specific heat standardizes that heat capacity value by saying, forget this difference between big objects and little objects. How much heat does it take to raise the temperature of 1 gram of that substance by a degree? In that case, the differences don't matter anymore. If they're the same substance, they'll have the same specific heat. The difference between the energy is just merely how big they are. The one that's bigger is going to require more heat overall, but it's going to have the same specific heat value. Now I just need to measure how big they are to figure out the heat value instead. And so we can see that there is a relationship between specific heat and heat capacity. If I were to multiply the mass times the specific heat, that would give me the heat capacity of that particular sample of substance. But we rarely ask for that, because again, it's not terribly useful to us to have a known value specific to a very singular object. Now, we can also standardize heat capacity on a molar scale. And notice that the capitalization returns there because we are talking about a molar heat capacity. What we have included here is, if you look at the subscript, you can see that the subscript not only includes a P, the P being there for constant pressure, which is a contingency for all of these calculations. They have to be done at a constant pressure. Otherwise, we can't get to that equivalency between heat and enthalpy that we desire in the first place. But with molar heat capacity, we can see that we're talking about the energy required to raise the temperature of a single mole of the substance. So again, the idea here is very, very similar. We're looking at, instead of 1 gram, 1 mole. But a given substance is going to have the same molar heat capacity regardless of the amount of substance. So standardization is important because it allows us to do things like this, where we can look at these heat values, and because they are standardized to a mole or to a number of grams, we can actually calculate values of heat associated with transformations of those substances. And so when we have phase changes taking place, there are very specific enthalpy values associated with those phase changes. For example, the enthalpy of fusion, delta H of fusion, sometimes referred to as the heat of fusion. This is the amount of energy that it takes to convert a mole of solid to a mole of liquid of that same substance. We're talking about that conversion between solid and liquid. So going back to our heating curve example, this is the amount of energy per mole that it takes to convert the solid ice, snow, into water. And we can see, it might not be able to see it well on this table here, the heat of fusion for water is 6.01 kilojoules per mole. So for every mole of ice, it's going to take about 6 kilojoules of energy to convert that mole into liquid water. For vaporization, what we're talking about there is the conversion of liquid to vapor at the boiling point. Now for water, because water is volatile and can vaporize and evaporate at a variety of conditions, we'll see that the heat of vaporization for water does vary by temperature. But most commonly, we think of this last one here on the bottom because that's the heat of vaporization at its boiling point, 40.7 kilojoules. As you can see, the difference between 6 kilojoules and 40.7 kilojoules tells you just how tightly bound water is to itself in the liquid phase. And we're going to see that that's a trend between all of the heats of fusion and all of the heats of vaporization. But the gap is going to be biggest among the polar molecules. And this goes back to that intermolecular forces discussion we had in chapter 6. Strong intermolecular forces, much more likely to stay in the liquid phase, which means requires more energy to break those bonds, those attachments, and vaporize it. Now, for a variety of substances, we can see that if we're not talking about phase changes, they have heat capacity and specific heat values associated with them as well. And the values of those heat capacities, those specific heats, have a lot to do with whether they are a conductor of electricity or not of electricity, of heat. Are they good conductors of heat or are they poor conductors of heat? So you can see that, you know, for example, metallic substances like these all have relatively low heat capacities, relatively low specific heats, and that makes sense. Metals are extremely good at conducting heat. So since they're good at conducting heat, it's not going to take much energy to raise their temperature. And on the flip side, it's not going to take much energy to get them to lose all of that heat. You know, think about when you cook. You know, the reason our pans are made out of metal is not because metal is cheap, but because it's a really good conductor of electricity, a really good conductor of heat. And the advantages to that is that those aluminum pans or stainless steel or whatever you've got, they heat up really, really quickly. We cook in them. And then when we put them into the sink and pour water on them, it doesn't take very much energy. It doesn't take very much time for that pot, pan, whatever, to cool down again so that we can actually touch it. That's great. You do the same thing with water. You heat up water to 400 degrees. It's going to take 2.5 hours to get it back down to room temperature. And that's a difference in that specific heat value. The more energy it takes to get the temperature up, the longer it's going to take to get that energy back down again. So coming back to this heating curve idea, if we were looking at a question like this, how much energy would it take to convert 275 grams of snow to boiling water at 100 Celsius? We have to understand that this process would occur in 3 stages. The first stage would be that we had to convert the ice at the cold temperature to ice at the freezing point. The second part would be that we have to convert the ice to water. So if we're looking at the graph, number 1 is segment AB. Number 2 is segment BC. And number 3 would be segment CD, where we have to heat it from water at 0 to water at 100. There would be 3 stages to that. Now, we've already talked about that middle stage. Phase changes can be governed by their heat of fusion, if it's solid to liquid, or heat of vaporization, if it's liquid to gas. What about these stages that don't have phase changes? How do we calculate the heat generated or the heat that has to go in to the system there? I'm not exactly sure why I put this particular slide here instead of at kind of where I was leading, but this is the answer. Specific heat can be calculated from a measurement of heat transfer divided by mass divided by change in temperature. If we rearrange this equation, what we get is that the heat that is transferred is equal to the mass multiplied by the specific heat multiplied by the change in temperature. And again, if we are at constant pressure, that would also mean that this value of Q that we are calculating here would be our enthalpy change. So what this boils down to is that when we are talking about heat change calculations, there are basically 2 directions we go. If the temperature is changing, this is the equation that we're going to use. Q is equal to MC delta T. So going back to that heating curve calculation, calculation 1, we're changing temperature. Calculation 3, we're changing temperature. This is the equation that we're going to use. Calculation 2, phase changes. Phase changes happen isothermically, meaning that they happen at the same temperature. That's why we measure a boiling point or a freezing point, because at that point, you've got the 2 phases in equilibrium with each other. And so that temperature is maintaining a constant level while that conversion takes place. As soon as the conversion is done taking place, then we see the temperature spike up again if energy is being added, or drop again if energy is being taken away. So our calculation is thus let's roll that back to this heating curve. So we want to use Q is equal to MC delta T for both segment 1 and for segment 3. And so to do that calculation, we would need to know the mass, which we know, the specific heat, which we could look up, and the change in temperature. So just as a point of reference, let's go ahead and just do this first calculation, just so that we can be familiar with it. So this was 275 grams of snow. The specific heat for water in the solid phase is 2.11 grams per joules per gram degree Celsius. And our change in temperature, delta T is always final temperature minus initial. So our final temperature was 0.0 degrees Celsius. And we started at negative 18 degrees Celsius. So the change in temperature was 18 degrees, 275 times 2.11 times 18.0 would give to 3 significant figures a positive 10,400 joules. So it took 10,400 joules to convert that snow up to the freezing point. Now we still haven't unfrozen it. It's still ice, but it's now warmer ice, if that makes sense. For segment BC, we would be doing Q is equal to the number of moles N times the heat of fusion. Number of moles, 275, divided by the molar mass, 18.02, would give 15.3 moles. Heat of fusion, I'll have to go back a couple of slides for 6.01 kilojoules per mole. So 15.3 times 6.01 would be 92.0 kilojoules. So what we would end up doing is calculating all 3 segments and then adding them together to get the final total heat added. And that's more or less what we're being asked to do in this No, it's not at all. Hold on a second. This is going to look real bad on the YouTube. All right, so let's finish this one off, since we don't have another example like it. And I know that there are a couple assigned in your homework. So for the last one, it's going to look very similar to the first one. It's going to be 275 grams. The specific heat for water in the liquid phase is 4.18 joules per gram degrees Celsius. That's one you're going to end up knowing very intimately by the end of this thermochem unit, because almost everything we do is in water. And delta T here, we went from 100 degrees to zero, or excuse me, from 0 degrees to 100. So 100 minus 0 is 100. 275 times 4.18 times 100 to 3 significant figures is 115,000 joules, which would be 115 kilojoules. I'm going to go ahead and convert our first problem to kilojoules as well. And so if we were looking at the total energy, it'd be the sum of these three. 10.4 kilojoules plus the 92.0 kilojoules plus the 115 kilojoules. We would get Q in total 10.4 plus 92.0 plus 115 would be 217 kilojoules. So when you come up to these heating curve problems in assignment 2, this is how you would approach them. Now, if it's a cooling curve, all the calculations are the same. You're just going to see the opposite effect. In the temperature change ones, your delta T is going to end up being negative because the final temperature will be lower than the initial temperature. And so that means that heat's going out, which makes sense. If we are cooling, energy is flowing from the system to the surroundings to lower its energy. So that's going to be a loss of heat. For the heat of fusion, we just have to remember that we're flipping the process around. If we're going from gas to liquid or from liquid to solid, that heat of fusion will have the exact same value, just the opposite sign. So heating curves, all of your Q's should be positive. Cooling curves, all of your Q's should be negative. All right, any questions about these two types of calculations? All right, so let me ask you this question then. Let's say we were looking at the combustion of methane. You know, that reaction that takes place when you turn on your Bunsen burner. If we were to try to determine the enthalpy of this reaction, how do we go about doing it? Any thoughts? Ideas? Good. Okay. That's where our minds should naturally go, is if we try to do it experimentally, why don't we just take a beaker full of water, heat it up on the Bunsen burner, and see how much heat the water absorbs. Problem with that approach is all of the heat from your Bunsen burner going into the glass and the water in that beaker? No, heat's going out in all directions, right? So how much heat loss are we dealing with there? The better question is this: is there a good way to directly do this kind of evaluation? Yeah. So spoiler here, there isn't a good way to do it directly. We have to do it indirectly. And that's where Hess's Law comes in. So we talked a little bit about Hess's Law yesterday. We're coming back to it a little bit more formally today. The reason why Hess's Law works is because enthalpy can be described as a state function. And again, state functions, we don't really need to worry too much about wrapping our heads around. It's not one of those terms that we're required to know. But just know that when we say something's a state function, what it means is that its value is pathway independent. So I don't need to measure it directly to know what it is. I can measure it indirectly through other means. That's what matters. Just like if I was going to walk from here to the door, the distance between me and the door is going to be the same. I can measure it directly. Now, if I choose to walk this way around the desk, serpentine between all of your desks, and end up at the door, I have every means and ability to do so. That doesn't change the fact that from here to there is the same distance. And that's ultimately what we are measuring with enthalpy changes and reactions. And eventually, when we get to thermodynamics, your other thermodynamic functions are the same way. So what Hess's Law says is that if we know that we can carry out a chemical reaction through a series of steps, the enthalpy of the reaction that we're actually interested in is merely the sum of the enthalpies of all of the steps that got us there. And so if I can find the right combination of steps that get me to the reaction that I'm interested in, all I got to do is add the steps together, and that'll give me the enthalpy change for the reaction I want. So coming back to this concept, here's our chemical reaction that we are interested in. In this case, where we are getting tripped up in particular, already with the knowledge that things are difficult to measure this directly anyway, but it would be almost impossible to do that chemical reaction where we got water in the liquid phase instead of in the gas phase. So the enthalpy of combustion for methane is -802 kilojoules per mole. the enthalpy of combustion, or excuse me, the heat of vaporization is negative 88. To get the reaction I'm interested in, I need to add these two equations together. When I do so, the waters in the gas phase will cancel out. So add together the equations. I can add together the enthalpies. The overall enthalpy for the reaction we're interested in is negative 890 kilojoules. Because the two steps were negative 802 and negative 88. Add those two together, I get the negative 890. So what this allows us to do is this allows us to use what we can call a table of reactions. Let's say that there is a series of reactions that we know the enthalpy values to. And your book has appendices. There are other well-known tables of reactions out there that we could utilize for these exact purposes. The things to keep in mind: if we have to manipulate an equation to serve our purposes, we need to make sure that we do the same manipulation to the enthalpy value associated with that reaction. So what we mean by that is, if we flip the equation around, we need to make sure that we change the sign, flip the sign of that delta H value. If we multiply our reaction by 2 or 3, or by some fraction, half, third, quarter, whatever, we need to make sure that we do the same thing to the delta H value as well. And if this sounds familiar, it's because we did something very similar when we combined when we combined equilibrium constants together in chapter 14. The only difference there was, instead of multiplying the equilibrium constant by whatever we changed it to, we multiplied the exponent by that value. This is actually a little bit simpler. We don't have to deal with exponents here. We just straight up multiply, straight up divide. A lot easier. The other thing that we need to make sure that we do, and it's not listed here, but it should be, we need to make sure that all of the equations add up together to the thing that we desire. And with that, we want to add the note, we really need to pay attention to phases when we do this. Because there are some reactions where we can do things and they will give us a liquid, and in others where they'll give us a solid or they'll give us a gas. And we want to be mindful of that when we work. So let's do this example here together. Find the enthalpy change for the reaction below, given the following reactions and their delta H values. Now, the approach I take to this is I'm looking to play a game of matching almost. I want to find the correct substances and make sure that they match up, that they line up to the correct side of the equation. So for example, in my two equations, I only have one spot where I have PCl5, the pentachlorophosphorus here. And it's right here. Now, that phosphorus pentachloride is on the correct side of the equation. They're both on the reactant side, which is where they're supposed to be. Problem is, this reaction has one phosphorus pentachloride. The bottom reaction here has 4 of them. So I need to manipulate this equation. The manipulation I need to make is a 1/4 manipulation. Divide all the coefficients by 4 and divide the heat of reaction by 4. So this becomes a 1, this becomes a 1/4, this becomes a 10/4, which is 2.5. Now with this first equation, we might also be tempted to look at, oh wait, here's chlorine. I need chlorine on the other side of this equation. Let me flip it around. Problem is, I've already got chlorine on this side of the equation also. What I need to focus on is the phosphorus trichloride here. And in this first equation, the phosphorus trichloride is in the correct side of the equation. If I flip this around, I'll actually end up with the wrong answer. But again, I can see I've got 4 phosphorus trichlorides in this equation. I only need 1. So I'm going to need to do the same manipulation. Multiply everything by 1/4. 6/4 is 1.5. And that makes this one a 1. Now I forgot to do it for the bottom one. I need to do it for the top one as well. I need to divide those enthalpy values by 4 as well. So negative 2439 divided by 4 is negative 609.8 kilojoules. 3438 divided by 4 is 859.5 kilojoules. When I add these two equations together, I'll see that I've got 1/4 P4 on this side and 1/4 on that side, so they cancel. I'll also see that I've got 1.5 chlorines on the reactant side and 2.5 on the product side. So the 1.5 cancels and takes 1.5 of those with it, which is just 1. The net reaction, PCl5 in the gas phase. Everything else on the reactant side is canceled out. Is equivalent is PCl3 in the gas phase on the product side and 1 chlorine in the gas phase as well. This equation in red matches the equation I'm supposed to get. So we've done Hess's law correctly from a reaction standpoint. Now we just need to do it from an enthalpy standpoint, add together negative 609.8 plus 859.5 and I get positive 249.7 kilojoules. All right, any questions with this example? All right, let's move forward. Here's one for you to try. Find the heat, the enthalpy change for the reaction between nitrogen and oxygen to make nitrogen dioxide using the three equations below and their delta H values. So do the same thing that we did in the first example. Match it up. Find the components of the target reaction and try to line them up number for number and see if that gets us where we need to go. We'll come back in a couple minutes and talk about the correct answer. All right, let's see how we did. So for me, what I would be looking at first is I need a nitrogen, and I can see that the first equation has the nitrogen I need with the coefficient that I need. So this one we're going to leave exactly as is. I also need oxygen. So the oxygen I need is in this third equation. There's two problems with it. First of all, it's on the wrong side. And second of all, it's the wrong coefficient. So what I need to do is I need to flip this equation to get it on the right side. And I need to multiply it by 4 to turn the 1/2 into 2. And so what I'm going to do is I'm going to rewrite this properly so that I have exactly what I need. So that's going to be 4 hydrogens in the gas phase plus 2 oxygens in the gas phase, making 4 waters in the liquid phase. And the delta H for that would be negative 43.7 times negative 4, which would be positive 174.8 kilojoules. And so now that I've rewritten it, I'm gonna mark out what was there before so that I don't accidentally use it when I combine everything. So now I've got my oxygen in the right location with the right coefficient. And then lastly, I have the 2 nitrogen dioxides. This middle equation has the nitrogen dioxide I need. It's in the right equation. It's in the right part of the equation. It has the right coefficient. So I'm going to leave it as it is. So what should happen is if I've got everything arranged, I should be able to start crossing out the things that are in common. So I can see that I've got 2 ammonia on the left-hand side and 2 on the right. So they're going to cancel out. I've got 4 waters here and 4 here. So they're going to cancel out. And I've got 7 hydrogens in the products here. And I've got 3 in equation 1 and 4 in equation 3. So 7 total to match the 7 here. So those cancel out as well. So all that is left is the nitrogen in the gas phase, the 2 oxygens in the gas phase, and the 2 nitrogen dioxides in the gas phase. For my delta H, since I've already manipulated everything, I just need to add them together. -115 plus -142.5 plus positive 174.8 would give me -82.7 kilojoules. If we're being super strict about significant figures, we will need to round that to -83. Since our first value doesn't have a decimal place. All right, any questions about this example?